Welcome to Experimental Techniques in Material Characterizations, lecture number 20. So it's a lecture series on X-ray diffractions as a part number 4. In this part, we will deal with the essential part and safety features and the X-ray diffractometers. These are basically two parts of the lecture. So let's proceed towards the first part, which is the essential parts of X-ray diffractometers. So what are the essential part and what for they are being used? So the first part is the X-ray tube, which is basically the source of the X-ray. The next part is the incident beam optics. So what is the role of the incident beam optics? So it provides the conditions the X-ray beam before it had the sample. What is incident beam optics? So incident beam optics is the condition the X-ray beam before it has the sample. Then another part we have is called the goniometers. So what is the goniometer? The goniometer is the platform that holds and moves the samples, optics, detectors, and the tube. Then we have the sample and sample holders, uh, receiving sides optics. So what is that? Is against like the conditions the X-ray beams after it has encountered the sample. Here we have two types of the two types of the optics. One is incident beam optics, and then is the receiving side optics. So incident beam optics is the condition the X-ray beam before it had the sample, and a receiving side optic is the condition the X-ray beam after it has encountered the sample. We have two conditions for for the optics. One is before it had the sample, for the X-rays before it had the sample, and after the X-ray, it's encountered the sample. And we have the detectors. What is the purpose of the detectors? Detectors counts the number of the X-rays scattered by the sample. So most of the powder diffractometers use the Bragg Bertano focusing geometry. So here you can see the typical geometry. This is called Bragg Brentano focusing geometry. So here you can see that we have the different parts, and it's something like the sketch of the experimental process. When we operate the process, or when we perform, or when we run the samples in the diffractometer. So here you can see that this is the point F, which we denoted by F. This is basically the X-ray source. So this is the X-ray source. Then we have another important part that we have denoted by DS. What is DS? This DS is basically the incident beam divergence limiting slit. So this one is the divergence limiting slit. And then we have two parts. One is at the X-ray source side, and the other is on the detector side. Here you can see that that has been denoted by SS1 and SS2. So what is that? So this part, this is basically the solar slat assembly. This is the solar slat assembly. So here one we have uh, on the X-ray tube side, and the other is on the detectors side. Then we have the sample. In the sample, it's lying here in the center. It's been denoted by S. And then another important part, it's lying here. That's been denoted by RS. So what is it? It is the diffracted beam receiving slit. So it's another slit. It's been denoted by RS. This is the diffracted beam receiving slit, and this part, which is denoted by C, is the monochromaters crystals. It's a monochromater crystal, and this part, which is denoted by AS, is basically the anti-scatter slit. So these are the different part of Bragg-Berthano para focusing geometry. So it's been used, which you can say some most of our powder diffractometer use. I mean, this is the technique of the geometry which most of our powder diffractometer they use. So a point detector and sample are moved so that the detector is always at a 2 theta, and the sample surface is always at theta to the incident X-ray beam. So here you can see that is the conditions that the sample is always at angle theta to the incident beam, and detector is always at 2 theta angle from the sample. And the para-focusing arrangement which you people you can analyze here, you can see by yourself. The incident and the diffracted beam slit moves on the circles that is center on the sample. So here you can see that these are the slit. uh, so the incident diffraction beam slit that moves on the circle. This is the circle that is centered on the sample. So here you can see the sample. So the divergent X-rays from the source hit the sample. I mean, here you can see it, and at different point. I mean, you can see that the sample is being hit at different point on its surface. So during the diffraction process, the X-rays are refocused at the detector slit. So here you can see that. And this arrangement provides the best combinations of intensity, peak, shape, and angular resolutions for the widest number of the sample. So X-ray radiations for the diffractions measurement is produced by a sealed tube or a rotating anode. So here you can see different part of the the X-ray setup, or you can see that the diffractometer. So here you can see that all these parts they are being clearly mentioned here in this sketch. So we have a sealed X-ray tube. They tend to operate at a power that lies in the range of 1.8 to 3 kilowatt. So that's the typical power that is need to run this apparatus. And then you can see it here. We have different power. Here this is the rotating anode, which is called rotating anode X-ray tube that produces much more flux because they operate at 9 to 18 kilowatt. So this is the rotating anode. It's been made of copper. So a rotating anode spin the anode at 6,000 revolution per minute, helping to distribute heat over a large area, and therefore allowing the tube to be run at a higher power without melting the target. And one reasons that we can make it safe for being melting, uh, so is that here we provide the cooling condition. I mean, here you can see that H2O in and H2 out. I mean, we provide the water resources so that we can keep it cool. I mean, we want to prevent that from melting. Then both the sources generate X-rays by uh, by striking the anode target uh, with the with an electron beam from a tungsten filament. So here is a filament. You can see it here in this setup. In this filament, all this setup is in a high vacuum, and you know that why we need a vacuum, that we have already mentioned in some of the previous lecture. So here we have a cathode filament. When we heat it with the power supply, so it emits the electrons. These emitted electrons, they hit this carbon anode, and are when it strike the carbon anode, so emit the X-rays. So here we are saying that both the sources generate X-rays, uh, and the reason for that is the X-rays being emitted by striking the anode target, with an electron beam from a tungsten filament. So the target must be water cooled. Why it must be water cooled? Because if we do not cool it down with the water, so after when it reaches to particular temperature, so this anode it will start melting. And another precautions for the filament, this filament, I mean this target which is being made of copper, and this filament which is being made of tungsten. So these both of them must be contained in a vacuum. So the wavelength of the X-rays is determined by the anode of the X-ray source. So here you can see, I mean, to clarify your concept of X-ray productions, which you already know from your basic class physics, that how X-ray is being generated. So it's the setup. I mean, the typical X-ray productions process. And here you can see that why we call it K alpha or K beta, or y k alpha 1 k alpha 2. So you all are well aware of these kind of the concept. So electron from the filament strike the target anode, producing characteristic radiations where the photoelectric effect. So here you can see the arrangement of the photoelectric effect. I don't need to explain that in full details because a well understood concept. The anode materials determines the wavelength of the characteristic radiations. According to that, I mean, it's been labels K alpha 1, K alpha 2, K beta, and K gamma, and so on. So that is being determined with respect to that particular arrangement. So while we would prefer a monochromatic source, the X-ray beam actually consists of several characteristics wavelength of the X-rays. I mean, we normally need a monochromatic source, but all as we cannot get that monochromatic source without any further arrangement. So we have to do several other arrangements to get the monochromatic X-rays. And what kind of the X-rays that's been utilized or they are being frequently uses during the XRD analysis, or we can say that what sort of the wavelength for the X-ray radiations are being utilized. So the wavelength for the X-ray radiations are sometimes updated by some of the prominent researchers who are working in the field. So here you can see it in this tables. uh, we have the radiations from different materials. The X-rays from different materials. They are being utilized. People that have utilized copper anodes, and some of them that utilize molybdenum anode, and also chromiums and cobalt anodes. They are being utilized, and they are being often quoted values from the Quality, that is the book that's published in 1956, and Bear that's been published in 1967. So the values from Breathen are reprinted in the International Table for X-ray Crystallography and most XRD textbook. But more recent values are from Holzer. Here you can see that these are the values from these are the values from the Holzer, all these. And these are the most recently utilized values. And you know that XRD, we also have the XRD software that's been utilized to update the values of these kind of the X-rays according to the most recent research. So here you can see the values according to different researcher. If you utilize copper anode, so K alpha, copper K alpha, K beta, and K alpha 2 and K beta will have the value of this much according to Berdin. According to Berdin, these must be the values of the X. These must be the wavelength from the X-rays from the copper anode. These are the wavelength of the X-rays from the if you utilize anode as a copper. So this is according to Berdin, and the same been analyzed by Holzer. So according to the Holzer, the value must be like this much. So here you can see that we have a minute difference between these values. So similarly, if we utilize cobalt anodes, from the cobalt, the K alpha 1, K alpha 2, and K beta, according to Bardeen and Holzer et al. I mean, again, is given here. So you can also check here the difference in the values. Then similarly, if we use molybdeniums or chromium anode, so according to Bardeen and Holzer, again the values they are being given. So here the people normally confuse that what sort of the values we should utilize, or we should we should consider as a standard. Don't worry for that. All these values they are being mentioned for the particular setup, for the particular for the particular diffractometer which you utilize. So Bardeen is quite old. From 1967, and Holzer is almost the updated value. So normally the people think that the Holzer one is the more reliable because it's the more recent one. Uh, Now let's move towards some safety precaution or some safety measures while dealing with the X-ray diffractometer. So the X-ray shutter is the most important safety device on a diffractometer. So here we will deal with the different part of the X-ray. The safety precaution or the safety measurement, or the other type of the arrangement that we can use with the X-ray diffractometer in order to keep ourselves safe during the XRD analysis. So here we can see we have the X-ray shutters. So what is the role of the X-ray shutters? So here you can see X-ray exit the tube through the X-ray transparent beryllium window. So this is the beryllium window. So X-ray emit through this window. One window we have on this side, and one window here on this side. So beryllium window, and we remember this is the X-ray transparent beryllium window. So the X-ray emitted through these windows. So X-ray safety shutters, here you can see that we have X-ray safety shutters. One shutter, this one in yellow color, and the other this one. This is the secondary shutter. So we have two shutters. So the X-ray safety shutters contains the beam so that you may work in the diffractometer without being exposed to the X-ray. So that is the main purpose of the shutters. So being aware of the status of the shutter is the most important factor in working in the safe environment, are working safely with the X-ray. So the shutters, you should know, you should frequently check the condition of the shutter while you are working with the X-ray diffractometer, because sometimes if it's not in proper working conditions, so it may create some health problem for the people who are operating the apparatus. So the condition of the X-ray shutters is very important, especially for the people who are working with the X-ray diffractometer. So the X-ray beam produced by the X-ray tube is divergent. The accident beam optics are used to limit this divergence according to the relations, that is lambda is equal to 2d sine theta. So that's the relations that's been used to limit the divergence of the X-ray. So X-ray from an X-ray tubes are divergence, contain multiple characteristic wavelength as well as Bremsstrahlung radiations. Neither of these conditions suit our ability to use X-ray for our analysis, because the divergence means that instead of a single incidence angle Q, the sample is actually illuminated by photons with the range of the incidence angle. And as a result of that, the spectral contaminations, we have spectral contaminations, which mean that the sample does not diffract a single wavelength of the radiation. I mean, we have multiple radiations That's why we have mentioned in the previous slide that we can have K alpha 1, K alpha 2, or K beta. But I mean that, and we also mentioned that a different condition what should be the wavelength of those radiations. So consequently, a single set of the crystallographic planes will produce several diffraction peaks instead of one diffraction peak. So optics are also used, and the purpose for the optic are to limit the divergence of the X-ray beam, to refocus X-ray into the parallel path, and to remove unwanted wavelength. I mean, it's the key purpose for using the optic and the X-ray diffractometer. So the first purpose is to limit the divergence of the X-ray beam. The second is to refocus X-rays into the parallel path, and to remove the unwanted wavelength. So the divergence light are used to limit the divergence of the X-ray beam. So here you can see that we have these slit. These are called the divergence slit, and the purpose of these divergence slats are to limit the divergence of the X-ray beam. So the slit block X-rays that have too great a divergence. Along with that, the size of the divergence slit influences peak intensity and peak shape. So that's why we always need a narrow divergence slide, because it reduces the intensity of the X-ray beam. Along with that, it reduces the wavelength of the X-ray beam hitting the sample, and produce sharpened peak. So the instrumental resolution is improved, so that closely spaced peak can be resolved. So one byproduct of the beam divergence is that the length of the beam illuminating the sample becomes smaller as the incident angles become larger. So here you can see that by yourself. That is the condition. So the length of the incident beam is determined by the divergence slit, goniometers, radius, and incident angle. I mean, these are the three conditions which determine the length of the incident beam. The first one is the divergence slit, goniometer radius, and incidence angle. So this should be considered when choosing a divergence slit size. So what we should consider? We should consider the following. These are the things which we should consider when we are choosing a divergence slit. That is, if the divergence slit is too large, so the beam may be significantly longer than your sample at a low angle. So here you can see the example. And the second condition is, if the slit is too small, so you may not get enough intensity from your sample at higher angles. So Appendix A and the SOPs contain a guide to help you choose a slit size. So you can see a manual. So you have manual always with your diffractometer. So that actually guide you about the SOPs, that what kind of slit you can use to get the best of the results for your sample. So the width of the beam is constant. That is, it should be 12 millimeters for the Regaco RU300. So this is the width of the beam with the Regaco apparatus. I mean, if you have Regaco diffractometers, so for that the width of the beam is 12 mm. Other optics that we utilize that limit the divergence of the X-ray beam is divergence limiting slats, parallel plates, collimators, and solar slat. So all of these you can visualize here. So these are being the parallel plate, collimator, and solar slats that block the divergence X-rays. I mean, here you can see that these are parallel plate collimators and solar slat, and their purpose here you can see we have a lot of divergence X-rays. So their purpose is
I mean the purposes of these parallel plates, collimators, and solar sled is that I mean they block the divergent X-rays, but it do not restrict the beam size like a divergence slide. So this is the key advantage of using this collimator and solar sled. I mean they block the divergence X-rays, but they I mean they do not restrict the beam size like that we have with the divergence slide. And we can repurpose X-rays into parallel beam. That is, we can utilize parallel beam optics. I mean, this is the one options for I mean to overcome the the divergence X-rays. And the second option is I mean to refocus X-rays into parallel path. So for that we use parallel beam optics. So here you can see we have parallel beam optics. So and these parallel beam optics, they are being parallel parabolic mirrors and parallel lenses. So focusing mirror and it's also consistent in the focusing lens, focusing mirror and focusing lens. So here you can see that so global mirrors and capillary lenses collect a large portions of the divergence beam. Here you can see that and refocusing it into a narrowly parallel beam. So here you can see that as a X-ray source where we have a lot of a large portion of the divergence beam, and after that I mean it's been focused into a narrowly parallel beam. So remove unwanted wavelength. That is, we can have monochromaters, and we can also have here we can also have K beta filters. So monochromaters remove unwanted wavelength of the radiations from the incidence or diffracted X-ray beams. Diffractions from a crystals of monochromaters can be used to select one wavelength of the radiations and provide energy discriminations. And incident beams monochromaters might be used to select only K alpha 1 radiations from the tube source. Uh, a diffracted beam monochromator, such as on the Rigaco RU300, may be used to remove fluorescence photons uh, K beta or tungsten contaminations photons from reaching the detectors. So without the RSM slat, the monochromators removes almost 75% of the unwanted wavelength of the radiations. So when the RSM slat is used, over 99% of the unwanted wavelength of the radiations can be removed from the beam. So that's all we have for this lecture. Thanks for watching. But stay tuned for the next lectures about the sample preparation for the XRD. So stay tuned. Till then, bye bye.